Welcome to The Explainer. Today we're tackling one of those topics in computer science that sounds super intimidating, but is actually incredibly powerful once you get it: dynamic programming.
You know those problems, right? The ones that just seem to explode in complexity, where the work just grows and grows exponentially. But what if I told you that hidden inside a lot of these impossible-looking problems, there's a really clever shortcut?
So, to really get this, let's start by walking right into a classic trap. Seriously, this one is set by a very familiar problem, and it fools countless programmers. I mean, look at this. A simple recursive formula, like the one for the Fibonacci sequence, it looks so neat, right? So elegant. But here's the thing. It's hiding a crazy amount of work, because we end up calculating the same values over and over and over again without even realizing it.
Okay, so how much work are we talking about? Well, to get just the 10th Fibonacci number this way, the function has to call itself 177 times. No joke, 177 times. That is a ton of wasted effort for such a tiny result.
So how do you get out of this mess? Well, the secret, the shortcut, is all about spotting just two hidden patterns in how the problem is built. If you can find them, you can take a problem that looks like it's exploding and bring it right back down to earth, from total chaos to something manageable.
All right, so let's get into these two patterns. Honestly, if you can burn these into your brain, you've basically got the key to the whole thing.
First up is something called optimal substructure. It sounds fancy, but the idea is simple. Think about a jigsaw puzzle. The best way to solve the whole thing is to first solve the little sections perfectly, right? You put together the corners, the edges, and those optimal little solutions build up to the optimal big picture.
And here's the second piece: overlapping subproblems. Now this is the real culprit. This is where all that wasted work comes from. Sticking with our puzzle analogy, it's like you saw the top left corner, and then you forget you solved it, and you solve it all over again. It's just pointless. Okay, let's take these two ideas and go right back to that Fibonacci problem. This is where it's all going to click. Get ready for that aha moment. So on one side, you've got this chaotic, branching mess of calls. That's our naive way. But on the other side, we do something super simple but powerful. It's called memoization, which is just a fancy word for remembering stuff. All we do is save the answer to a subproblem the first time we figure it out. Then, before we calculate anything, we just ask, hey, have I solved this before? If the answer is yes, we just grab the result. And just like that, the work totally collapses from that crazy tree into a nice straight line.
And if you don't believe me, just look at the numbers. Here's the data for calculating Fibonacci of 10. We had 177 total calls, right? But guess how many of those were actually for unique problems? Just 11. 11! That means 166 of those calls were just wasted time. Our program was just spinning its wheels.
This chart just makes it so obvious. That big bar on the left, that's our 1,770 calls. And that tiny little bar on the right, that's the 11 problems we actually had to solve. The huge gap between them, yeah, that's all the work we just eliminated. That is the power of this approach.
Okay, so that works great for Fibonacci. But how do you actually spot this stuff in the wild on a totally different problem? How do you build that instinct?
Well, here's a little four-step guide you can use. First, define your state. Basically, what's the smallest amount of info you need to describe a unique subproblem? For Fibonacci, it was just n. Easy. Second, find the recurrence. Can you write a formula that connects the big problem to the smaller ones? For us, that was our f of n equals f of n minus 1 plus f of n minus 2. Third, confirm there's overlap. You got to make sure you're actually resolving the same things. And last, verify that the best answers to the small problems actually build up to the best answer for the big one.
So at this point, a lot of people think, wait a minute, isn't this just a greedy algorithm with a fancier name? It's a really common question, and honestly, knowing the difference is super important.
Think about it like this maze. A greedy algorithm, that's like a runner who only looks one step ahead. At every intersection, they just take the path that looks best right now. It's fast, sure, but they can easily run straight into a dead end. Now, dynamic programming, it's smarter. It's more like mapping out the entire maze. It explores every path, remembers which ones are dead ends, and then uses all that information to find the absolute, guaranteed, shortest way out. So you see, the real trick here is knowing when to use this thing. It's a super powerful tool, but it's not the right tool for every single job. It's a game changer, but only when the conditions are right.
So when should you reach for DP? Well, here are the big signs. First,
The problem is asking you for some kind of optimal thing, the minimum cost, the maximum value, or maybe the total number of ways you can do something. Second, you can actually write down that clean recurrence relation. And third, the number of states, the number of unique subproblems, isn't totally out of control.
But, and this is important, it is not a silver bullet. If your subproblems don't actually overlap, if they're totally separate, then something like divide and conquer is way better. And hey, if there's a simple greedy solution that you know works, just use that. It's going to be easier to write and probably faster too.
Look, to get good at this, you just gotta practice. You have to build up that pattern recognition muscle. So get your hands dirty with these classic problems. Things like the coin change problem, longest common subsequence, edit distance, the knapsack problem. They're like the fundamental exercises. Each one teaches you something new, and that's why this stuff is so critical in fields from bioinformatics all the way to financial modeling.
So at the end of the day, it all comes down to this simple little mantra. 1. Can you identify a state? 2. Can you write a recurrence? And 3. Is there overlap? If you can say yes to those 3 things, you've probably, almost definitely found a problem where dynamic programming is your answer.
So now you know the secret. You know the patterns to look for. You've got the key to unlock a whole category of problems that might have seemed completely impossible before. So go find that shortcut.